All right, so reviewing 1,3-butadiene. So 1, 2, 3, 4 butadiene, right? Because we have 1, 2, 3, 4 carbons. 1 is where one pi bond starts. 3 is where the other pi bond starts. 1, 3 buta, 4 diene, 2 alkenes. So what is in this system? We have how many electrons are in this p orbital system? How many electrons total? 4 electrons. And you got that number because there's how many pi bonds? 2 pi bonds. And how many electrons in a bond? 2. Very good. So I went ahead and drew up the way these 4 p orbitals, right? There's 4 p orbitals, how they can line up. They can either interact in a constructive fashion or a destructive fashion. They can either share electrons or not share electrons. So in this bottom one, if this axis here is energy, this would be the lowest energy type of bonding interaction, right? The orbitals are all in the same phase, right? They're all in the same phase, so they're all forming pi bonds. Right? All of these, if you think of these as waves, they're all interacting positively, constructively. They're all sharing electrons. Right? So we have 4 electrons. I put my first 2, right, in the lowest energy orbital. I put my next 2 in the lowest energy orbital. Now, why is this a little higher in energy? Well, let's look at it. There's a bonding interaction where the p orbitals share electrons. There's an anti-bonding or a non-bonding interaction. There's a node where they can't share electrons. There's another bonding interaction where they share electrons. So overall, it has a 2 bonding and 1 non-bond, 1 anti-bonding. So overall, it's a bonding interaction. So I put electrons in there, and that's still a good thing, right? Putting electrons in something where it's overall bonding, that's a good thing. That's stabilizing. Now, once I go up one more energy level, but we can see why this is higher in energy because it doesn't have as many bonding interactions as this. But now if we go up one more level, now all of a sudden we have a node, a bonding interaction, and then another node. So can't share electrons, can share electrons, can't share electrons. All of a sudden now we have 2 nodes and 1 bonding interaction. Overall, now this is an anti-bonding interaction. So a lot of times we'll draw kind of this demarcation line between, right, bonding molecular orbitals versus anti-bonding molecular orbitals. All right. And then as you go up another level, right, you can see you can start changing the phases where now there's no bonding interactions at all, and it's both node, node, and node. Right. So no electrons are being shared in that orbital, and that's the highest energy orbital. Right. So none of those waves are interacting constructively. So the way we think about this, right, what we really care about is these electrons and empty orbitals kind of in the middle, right? We want to find the highest energy electrons. We call that the HOMO, the highest occupied molecular orbital. And that's interesting because those usually are the nucleophiles, right? The electron rich. Those are the electrons that do the reactions, right? Those are electron rich. When you've done all those pi bonds acting as nucleophiles, we were talking about these electrons in this molecular orbital, right? What if we want to think about a pi bond as an electrophile? Then we look at its LUMO, right? Its lowest unoccupied molecular orbital. Lowest unoccupied molecular orbital. That's an electrophile, right? So every bond, right, at some level, right, can be a nucleophile or electrophile depending on which molecular orbital you're using. All right, so if you want to break a pi bond, what do? You put electrons in its LUMO. If you want to use a pi bond as a nucleophile, what do? You use its HOMO electrons, its highest occupied molecular orbital electrons. And that's the big difference in energy. All right, this is more complicated than we've seen sigma star. Maybe an easier one that we've done, or a less complicated one, could be a sigma bond. So in a sigma bond, you have a sigma bond and you have a sigma star. Right? In a sigma bond, how many electrons are there? 2. So you have 2 electrons in the system, so it's one sigma bond, and there's 2 electrons. So we fill the electrons in here, because this again would be energy. So there's our demarcation line between bonding and anti-bonding. The sigma bond, right, if I did this in red, most of the electron density in the sigma bond is around the bromine, right, because it's more electronegative. Where's sigma star going to be at? It's going to be more around the less electronegative carbon. That's where sigma star is at, and that's what sigma star looks like. It's just opposite that. Right? So we've seen this before, right? If I want to break this sigma bond, I put electrons into sigma star, and that would break this sigma bond. And then the final example I showed in class was, what if you have a carbon-oxygen pi bond? You draw it like this. How do we think about like a ketone, the carbon-oxygen pi bond? So again, when we think about this, we say, okay, how many electrons are in that pi bond? 2 electrons. And it's 1 pi bond. But it becomes a little more complicated now, because before, butadiene was all carbons, right? So there's no electronegativity difference. So these are all the same size. But it's more related to this carbon-bromine now, because now there's an electronegativity difference. So we need to think about, if we draw the pi bond, and there's still pi star, right? So there's going to be our demarcation line. This will still be energy, right? The antibonding orbital is always higher in energy than the bonding orbital. We put 2 electrons in the pi bond, right? Because there's 2 electrons, that's where they'll go. Lowest energy first. But now, what does the pi bond look like? That's going to be a little different here. In the pi bond, in the bond, who owns the electrons? Carbon or oxygen? Oxygen does. So let's make oxygen have a larger orbital, right? Showing that basically that's saying the electrons are more by the oxygen. That's all it's saying, right? Similarly, how we did the sigma bond here, notice how it kind of leans towards the bromine, not towards the carbon. So the carbon orbital here should be, a little smaller. Still a bonding reaction, but it's smaller there because the carbon doesn't own the electrons in the bond. But now in the anti-bonding sense, where are the electrons more likely not to be at? They're more likely to not be at the carbon. So now that gets the bigger picture, the bigger lobe, and the oxygen gets the smaller one. And we got to be careful, right, to show that there's a node there. The electrons can't be shared. But the size of the orbitals also starts to come into play. And this makes sense, right? Because when you're going to react with a carbonyl, where does the nucleophile go? If I have a nucleophile, if I have a Grignard, if I have a MgBr, right, where do the electrons go? They go to the carbon. That makes sense, right? Because that's where it's most delta plus. That's where the bigger antibonding orbital's at. So taking a look at a sapling question. Here we have a diene, and the question is, draw the intermediate and product structures, including any formal charges, and they want the most stable resonance form. So we got to choose between these pi bonds. So let's number them. 1, 2, 3, 4. Which pi bond, when it reacts, is going to give us the most stable carbocation? The pi bond between 1 and 2, the pi bond between 3 and 4? Between 1 and 2. And where do we want to put where is the new CH bond going to be formed at? Which carbon? Carbon 1. So the plus charge will be on carbon 2. Very good. Right? Pi bond's a nucleophile. The HOMO, the highest occupied molecular orbital of the pi bond, is actually the nucleophile. It's going to attack sigma star of the hydrogen-chlorine bond, breaking the sigma bond. So what's that first carbocation going to look like? And the plus charge there. Renumber our carbons, 1, 2, 3, 4. Plus, we have what else left over to balance our charge? Cl minus. So at this point, right? This is a what kind of carbocation do we have here? Tertiary and allylic. Good. So tertiary allylic is really stable. So one of the products could be the chlorine just reacting with a carbocation. That would give that. The chlorine can come from the top or the bottom, so we'd have this. We have both enantiomers. Right? We'd have both enantiomers. But the other question says, the part of this question says they ask for the less stable resonance form. So let's maybe redraw the original tertiary allylic carbocation. Can we draw a resonance form for this? We can. Yep. So anytime you have a carbocation, you can do rearrangements and resonance for sure. So resonance arrow. And now the plus charge, or new pi bond between which two carbons? 2 and 3. Plus charge there. Chlorine still, right? Cl still along for the ride. 1, 2, 3, 4. Chlorine reacts. Again, both enantiomers are formed. 1, 2, 3, 4. What kind of product did we just form? That's the 1,4 product. What was the first product we formed? The 1,2. Is there a difference between the kinetics and thermodynamics? So the 1,2, so there's two different intermediates. So we have, let's label these. This is going to be intermediate A. This can be intermediate B. If I were to draw a free energy diagram here, energy, same starting materials. Which intermediate is more stable, A or B? A, so that would be lower. So we'll put intermediate A here, and that means intermediate B is higher in energy. We said that because this is secondary in allylic, right? Versus tertiary in allylic. What about the products? Is one product more stable than the other? Which product is more stable? The 1,4 looks like it's more stable. Why did you say the 1,4? More substituted alkene, right? The Zaitsev rule. So we'll put the 1,4 here, and then the 1,2 would have to be a little bit higher. It's all relative. So the 1,4 comes from which intermediate? The B, right? So higher energy, or we'll get there. Higher energy intermediate. So it'll take more energy to get there. Both to get to the more unstable intermediate. But then to get to the more stable product, the kinetic one is the 1,2, gets to the lower energy intermediate, and then to the higher, energy product. Right? So when we think about these reactions, we want to think about conditions. Right? If we ran the reaction cold, what product would we most likely make? If we ran the reaction cold, we'd make the 1,2, the kinetic product, right? This is going to be the kinetic product, the 1,2, because it comes from the lower energy transition state and also the lower energy intermediate. If we heat it up a bunch, what product should we make? Probably the 1,4, right? But the 1,4, the reason that takes more energy is because the 1,4 comes from the less stable intermediate, right? So, and the less likely intermediate. So, there you go. So a good question is, will initially this 3,4 bond ever break? It will not, right? I should actually draw another step in here, right? Everything goes through intermediate A, and then it goes up to, you have to go up to intermediate B. So this 3,4 bond is never really going to break because you're always going to try to form the most stable carbocation first, right? So you're never really going to break this 3,4 bond. That's right. I'm actually going to fix my free energy diagram. So I don't like this free energy diagram. It had some good ideas, but there's a problem with that because, right, you need to make intermediate A first before you even make intermediate B. So let's reimagine our free energy diagram. Let's fix this. Because you can't make intermediate B without first making intermediate A. So let's take a look at maybe how we do this a little differently. So let's draw them in there again. So intermediate A is lower in energy. So here's intermediate A. And we're going to need some energy to get to intermediate A. Sometimes from intermediate A, you're immediately going to just go right to the 1,2 product, right? So you go right to the 1,2 product, and that means the chlorine is just going to react, and you're going to be done. Make that 1,2 product. Other times from intermediate A, if there's enough energy, what you're going to do is actually get up here to intermediate B. So there's enough energy, sometimes you can go up to here. Not very likely, but then once you get to intermediate B, the only product you can make then is back down to the 1,4. So some people might say, well, how the heck are you ever going to make the 1,4? Let's say you make the 1,2, and this hill back up isn't that high, right? Just even going, right, because the reaction can go forward and backwards. The hill back up here isn't that high. And sometimes, I don't know, just luck. You get up there and you make intermediate B, and then it collapses down to 1,4. And if you ever make this 1,4, look how high up the hill you have to go to get back out. So it's not so much that is how likely is the 1,4 reaction to form. It's a matter of time and energy. So, right, you run this reaction, you're going to probably the first 10 minutes, let's say, you make all 1,2. But if you let it keep going and you really heat it up, really the 1,2 product can start going back to intermediate A. And then if there's enough energy around, something happens, we can get up to intermediate B, and then that can collapse down to 1,4. And then no matter what we do, once you're down at the 1,4, you're never climbing back up that hill. Right? Does that make sense? This is a better picture of what's going on there. Right? Always be thinking about these things in these free energy diagram terms. All right, so we're going to talk a little bit about the Diels-Alder reaction. The Diels-Alder reaction is a really important reaction, a really famous reaction, won the Nobel Prize in 1950. It has to do with the reaction of a diene, 1, 2, 3, 4, a diene, and 5, 6, a dienophile, a lover of dienes, right? A ophile means a lover of dienes. So a diene and a dienophile, and they come together to form a 6-membered ring. We call this a cycloaddition reaction. Cycloaddition. Because in this reaction, we form 1 new pi bond and 2 sigma bonds. All right? And we start with 3 pi bonds and end up with 1 new pi bond and 2 sigma bonds. That's a cycloaddition. So let's number our carbons to see where those bonds are at. So what's the new pi bond is between C2 and C3. What's the other new sigma bond is between C1 and C6. And the other one is between C4 and C5. That's right. So those are new bonds that are always formed. What you can start to look for is this 6-membered ring. All right? 6-membered ring. All right? We're going to take 3 pi bonds. We'll start with 3 pi bonds. So we're going to start with 3 pi bonds in the cycloaddition. 3 pi bonds. And they're going to be turned into 1 pi bond and 2 new sigma bonds. It has to do with the diene and the dienophile coming together to make those bonds. It's always the same thing. What do the arrows look like? So these are cycloadditions, so there's really not a nucleophile electrophile. The electrons in these p orbital systems, these pi bond systems, just kind of come together. They come together to form these bonds. So it's like think of like a cyclone of electrons coming together to form these bonds. But you still can draw some arrows to show it. Goes there. And then it comes back around. So it's 3 arrows of electrons kind of cyclizing together. You can see the new C1, C6 sigma bond, the C2, C3 pi bond, and the new C1 to C4 to C5 sigma bond. That's the basic reaction of the Diels-Alder. A diene and a dienophile come together, start with 3 pi bonds, and out comes 1 pi bond and 2 sigma bonds. Another thing you look for, the new pi bond always forms on the diene side where there wasn't a pi bond before on the diene. Okay, so that's the basic thing to look for. Yeah, the electrons could flow. You could have gone from this way. You could have flowed the electrons either way. As long as you have the 3 arrows, they could go different. As long as they're going the same direction, right? Be careful, right? The electrons always flow in one direction or the other. So they could have flowed to the left, or they could flow to the right. But they have to flow in the same direction always, right? This has to be a circle. Cycloaddition. Cycloaddition. So don't have some electrons going back at each other. Cycloaddition. And this could be any pi bond, right? I said pi bond. Does that mean could this be an alkyne? It could. All right, so a basic one. Let's see what happens if what happens if the dienophile is actually an alkyne. So do our numbering system again. 1, 2, 3, 4, 5, 6. What kind of product is that going to form? Sorry, the electrons. I did this time. I flowed them this way. Pi bond attacks, forms a new sigma bond. New pi bond formed. Pi bond breaks, new sigma bond formed. So we always know on the diene side there should be a new pi bond, right? So there should be, if I number my carbons again, 1, 2, 3, 4, 5, 6. Where should there for sure be a pi bond? Between 2 and 3. Should there be another pi bond somewhere? Where at? 6 and 5. Very good. Very good. Now this is where it gets, so that's great. Perfect. Because the same thing, it's still cycloaddition, right? What happened? We took 3 pi bonds, and we end up with 1 new pi bond and 2 sigma bonds. These are all new bonds. 1 new pi bond, 2 new sigma bonds. This pi bond, just along for the ride, right? On the alkyne, the dienophile. The lover of dienes, the dienophile. Right, but now the other hard part for this is, what you're going to need to do is not just look at the star materials and make the product. You need to be able to look at, oh, here's a ring. Do you know what the star materials could have been? Can you work backwards? So let's try that. All right. What if I gave you something like this? What could the starting materials been if this was from a Diels-Alder reaction? What would the diene and dienophile be? There's actually more than one option here. So I've drawn both. I've drawn the same thing twice because there's actually 2 ways you could do this, 2 ways to analyze this. So working backwards, retrosynthetic arrow, working backwards. I know my dienophile always has, right, the pi bond there in between. So let's number it like this. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. The bonds I'm looking at, the sigma bonds I'm looking to break in each case. In this case, I'm saying I'm breaking those 2. In this case, I'm saying I'm breaking those 2. So my diene is there, and my other diene is there. So my basic diene structure, and this first one would be like this. 1, 2, 3, 4, plus my dienophile is going to be what? What's my dienophile going to be? What kind of functional group is it going to have? Alkyne. 5 and 6, and then I can't forget, right, these 2 carbons, right? Don't forget those 2 carbons. They're obviously there too. So this would be the diene and the dienophile. One possibility to make this. What about the other possibility? What would that look like? Draw my diene out. 1, 2, 3, 4. What else is attached to 2 and 3 in this case? The methyls are. So I need to make sure you have the methyls on there. That's one diene. Now what's my dienophile going to look like? It's just going to be a alkyne like that. 5 and 6. So 2 possibilities could work here. All right, 2 different ways you could do that. But you also want to, so my point is, you need to be able to look at products and tell me what the diene and dienophiles could be. What are the possibilities? All right, what about the situation we have here? We have the same diene, and we have a dienophile. One's a trans or a E dienophile, and the other one's a cis or a Z dienophile. They can't get the same product, right? Because trans is different than cis. They can't get the same product. But this, the fact that this is trans has to be somehow communicated into the product. It matters, right? Because this is all happening. How many steps is this taking? It's all happening at once, right? There's no carbocation forming, so we can't, right? Carbocations, we know, mess up stereochemistry and make it racemic. But this is going to stay. It's all happening in one fell swoop. So what's the product going to look like? So if this has 2 methyls, and those 2 methyls are trans to each other in the starting dienophile, in the product, they're also going to have to be trans. And you also make, right, the other enantiomer, you'd make this as well. So you make both of these products, right? Notice the methyls, one's up, one's down, because they're trans to each other. Now there's in a ring in trans. Make sure I add my carbon numbers. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Excellent. What if they're cis? What's it going to look like? Same 6-membered ring, same pi bond form, but now they're either both wedged or they would both be hatched and pointed down. Numbered again, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So whether something's cis or trans matters in the final product, right? With the wedges and hatches. Something's cis, they're going to be either both wedged or both hatched. If they're trans, they have to be opposite each other. Notice with the alkyne that we did before, right? Did it matter? Does it matter here? Because alkynes can't be cis or trans, so it doesn't matter. So this is called that stereospecificity. Stereospecificity. Meaning one stereoisomer, a trans, is going to give a different product than a cis. A specific isomer gives a specific product. Stereospecific.